You're looking up at the cosmos, maybe you've even spotted another world through a telescope, and your mind just goes wild, right?
Absolutely.
What else is out there? What bizarre kinds of planets are circling those distant suns?
It's captivating stuff.
We get it. You're curious and you want to wrap your head around some seriously complex ideas without needing a PhD. Well, that's exactly what we're up to today.
Yeah, we're diving deep into a really fascinating puzzle in the world of exoplanets.
A real head scratcher.
Indeed. We're focusing on a really peculiar type of planet called a hot Jupiter.
Hot Jupiter. Okay.
Now, the name gives you a hint, but what makes these celestial bodies so interesting is how they kind of challenge what we thought we knew about how planetary systems come together.
Exactly. So what are we actually talking about when we say hot Jupiter? It almost sounds like an oxymoron, doesn't it?
A bit like a frozen flame, yeah.
So the headline here is, these massive planets are showing up where they shouldn't be. Not according to our best understanding anyway.
That's the core mystery, yes.
So let's unravel that. What is a hot Jupiter, technically?
That's a great way to put it. Essentially, hot Jupiters are huge gas giants. Think planets about the size of our Jupiter or Saturn.
Okay, massive.
But they orbit their stars incredibly closely. I mean, really close.
How close are we talking?
We're talking orbital periods of just a few days, typically between, say, 3 and 9 days.
Wow.
And they're so close, within about zero point 0.1 astronomical units, or AU.
zero point 0.1 AU. Just for comparison, Mercury in our system is...
Mercury is about 0.4 AU from the sun.
Uh-huh.
So these hot Jupiters are 4 times closer, or even more.
Wow. That's practically buzzing the stellar tower. It makes you wonder, how on earth did they get there?
Exactly.
Because from what I gather, our current models of planet formation really struggle with that. They can't easily explain forming such massive planets so close in.
That's precisely the crux of the puzzle. Our current leading theory for how gas giants form is called core accretion.
Right, core accretion, building up from a core.
Yeah. The model suggests planets began as small rocky or icy cores in that swirling disk of gas and dust around a young star, the protoplanetary disk. These cores then pull in more and more material through gravity, eventually snowballing into massive gas giants. But this works best further out.
Why further out?
Well, particularly beyond what we call the snow line.
The snow line, okay.
In our solar system, that's roughly around 3 AU. Out there, it's cold enough for icy materials, water ice, ammonia ice, methane ice, to be solid and abundant. That gives you a lot more building material for those initial cores.
Ah, more stuff to build with.
Right. Closer in, inside the snow line, it's too hot for those ices. There's less solid material available.
And the heat itself is a problem.
Yes, and it's not just the lack of material. A growing planet, especially a big one, can actually carve out gaps in the disk around it.
Oh, right, you mentioned that earlier, like clearing its path.
Exactly. So it kind of isolates itself, making it even harder to hoover up more gas if it's trying to form in that inner region. Building a Jupiter-sized planet that close to a star is, well, it's like trying to build a giant snowman in the desert.
Okay, yeah. The raw materials and conditions just aren't right. Clear picture.
Precisely.
So if they couldn't have formed that close, the obvious next question is, did they move?
Bingo.
Is there some kind of planetary migration going on?
That's the prevailing idea, yes. If hot Jupiters formed further out, where core accretion works, say beyond the snow line, then something must have caused them to migrate inwards to their current very tight orbits.
Okay, so they're movers. How might that happen? What are the theories?
There are two main ideas, two main hypotheses about how this migration might have occurred.
All right, let's hear them. What are the cosmic highways that could have delivered these giants to their stars' doorsteps?
Okay, the first is called disk-driven inward migration.
Disk-driven. So the disk itself is involved.
Yes. The idea suggests that the protoplanetary disk, the gas and dust still swirling around, played a role after the planet formed.
Wow.
Well, there's a gravitational back and forth, a kind of dance, between the formed planet and the remaining disk material. This interaction can create torques.
Torques, like a twisting force.
Exactly, a twisting force. And these torques can cause the planet to gradually lose orbital energy and, well, spiral inwards over time, slowly moving closer to the star.
Interesting. So the very stuff they were built from could have also nudged them inwards.
Okay.
What's the second possibility?
The second main idea is a bit more dramatic. It involves a planet ending up in a highly eccentric orbit.
Eccentric meaning very stretched out.
Very stretched out, yeah. Like an oval, a very elongated ellipse, rather than a nice, neat circle.
Okay. So it gets flung onto this weird path.
Something like that. And if a planet finds itself on such an orbit where one end of its path swings it very close to the star,
Mm-hmm.
then tidal forces between the star and the planet become really important. Like the moon's tides on Earth, but much stronger.
Right. Massive gravity involved.
Huge gravity. These tidal forces can dissipate orbital energy, essentially acting like brakes, causing the orbit to shrink and become more circular over time.
So it gets circularized.
Yes, through tidal damping.
Yeah.
But the end result is a circular orbit that's much, much closer to the star than where it might have started.
Okay, so it's like the planet gets launched inwards on this wild, elongated ride, and then the star's gravity sort of tames it, pulling it into a tight circular embrace.
That's a good analogy, yeah.
But what could cause those initial highly stretched out orbits in the first place? That seems key.
Yes. This is where things get really interesting and where our sources, especially the research using data from the Gaia Space Telescope, become crucial.
Gaia, right, the mission mapping the stars.
Precisely. So one possibility for getting that high eccentricity is planet-planet encounters.
Like cosmic billiards.
Kind of, yeah. Planets within a system interacting gravitationally, maybe getting too close, and one gets slingshotted onto a very eccentric path.
Okay, what else?
Another is the influence of a distant stellar companion, like in a binary or triple star system. Its gravity can perturb the planet's orbit over long timescales through something called the Lidov-Kozai effect.
Lidov-Kozai, that sounds complicated.
It is a fascinating gravitational dance in systems with at least 3 bodies. It can pump up the eccentricity of one body while changing its tilt.
But you said Gaia is pointing towards something else.
Where Gaia's data is helping us investigate another major possibility, which is our main focus today based on the research: the role of close encounters with other stars.
Other stars, not just companions in the same system.
Right. Encounters with stars from outside the system, maybe when the system was young and still part of a star cluster.
Star clusters, so like a crowded cosmic neighborhood, could be messing with planetary orbits.
Exactly. That sounds plausible in a chaotic kind of way.
It does. The idea is that if a young planetary system, maybe just a few million years old, has a close gravitational encounter with another star passing by in a dense star cluster, that encounter could give a significant gravitational kick to one of the planets.
A kick onto that eccentric orbit.
Potentially, yes. Putting it on that highly eccentric path needed for the tidal circularization scenario we just talked about. Okay, that connects the dots. But there's a bit of a timing problem here, isn't there?
You're thinking ahead, yes.
Star clusters aren't exactly permanent fixtures in the galaxy, right? They tend to spread out, disperse over time.
That's true. Usually within, say, 1 billion years or so, maybe less, maybe more, depending on the cluster.
And many of the exoplanet systems we've observed, especially those with hot Jupiters, are much older than that.
Good point. They can be several billion years old.
So how can we connect events in a long-gone star cluster to planets we see today? The evidence seems like it would have vanished.
That's a really important point, and is a major challenge. But this is where the Gaia mission has brought about a revolutionary change in our perspective.
How so? What can Gaia tell us about these ancient clusters?
Researchers, like Winter and colleagues back in 2020, used data from Gaia's second data release DR2 to look for subtle links. They were hunting for stars that might have once belonged to the same cluster, even if the cluster itself has long since dissolved.
Finding ghosts of clusters past.
Sort of. Their method was to look at co-moving stellar groups.
Co-moving, meaning they're traveling together.
Essentially, yes. Stars that, even though they might be quite far apart in space now, still share very similar motions, similar velocities and directions through the galaxy.
Okay.
This is analyzed in what astronomers call phase space.
Yeah.
It's not just about position, where a star is, but also its velocity, how fast it's going and in what direction.
Right, position and motion.
Exactly. Think of it like tracking cars that were once in a convoy. Even after they've spread out on the highway, they might still be going roughly the same speed and in the same direction for a while.
Okay, I get that. The motion remembers the origin.
Precisely. Stars born in the same cluster get similar initial velocities. Even as the cluster disperses due to galactic tides and internal dynamics, that shared velocity, that motion fingerprint, can persist for a very long time.
So Gaia, measuring positions and motions with incredible accuracy,
Allows us to spot these groups of stars that are moving together, even if they're no longer clustered spatially. It's like forensic astronomy, tracing movements back.
Forensic astronomy, I like that. Tracing the movements of stars back in time to see if they were once part of the same cosmic family.
That's the idea.
And what did Winter and his colleagues find when they did this forensic work on planet-hosting stars?
What they found was quite significant. They looked at stars known to host exoplanets and checked if they belonged to these phase space density enhancements, basically, regions in this position velocity map, where stars are clumped together in their motion, suggesting a common origin, likely a dissolved cluster.
Okay.
And after carefully accounting for other factors like the star's age, mass, and chemical makeup, they found a striking difference.
What difference?
Exoplanet systems located in these phase-space density enhancements, the ones likely from former clusters, had planetary systems that looked different from those around isolated field stars.
Different how?
Specifically, the median semi-major axis, that's basically the average distance of a planet from its star,
Right.
were much smaller. And consequently, the orbital periods were much shorter in these denser co-moving regions. The planets were closer in, on average.
Closer in. And here's where it gets really interesting, isn't it? Did they find more hot Jupiters in these stellar reunions, these phase-space groups?
They did. That was the kicker. Their analysis showed that hot Jupiters were preferentially found in these phase-space overdensity regions.
Wow. So not just closer planets in general, but specifically hot Jupiters favor these regions.
That's what the data suggested, yeah. This strongly indicates that the environment matters. Those close encounters within young star clusters, or maybe just the overall dynamic environment of those clusters, could be a key factor, maybe even the dominant factor for some systems, in creating the tight orbits of hot Jupiters.
More important, perhaps, than just the disk migration or maybe planet scattering within isolated systems?
Potentially, yes. It adds a crucial environmental piece to the hot Jupiter puzzle. It suggests their formation or migration path is strongly linked to their birth environment.
Okay, so that's another piece of our hot Jupiter puzzle falling into place. The cluster connection seems strong.
It's a compelling piece of evidence indeed. But
Yeah.
the story doesn't quite end there.
Oh, call. There's more.
Well, the research also pointed out Winter and his team were careful about this, that old star clusters aren't the only things that can cause stars to have similar velocities, to cluster in phase space.
What else could do it?
Our galaxy itself. The Milky Way is a pretty dynamic place. It's not just a smooth, static disk of stars.
Right, it's got structure, spiral arms, a central bar.
Exactly. And Gaia data, especially starting with DR2 in 2018 and subsequent releases, has been incredible at revealing just how much substructure exists in the phase space distribution of the disk stars.
Substructure like.
We're talking about large-scale features, waves, ripples, streams of stars moving together. These can be caused by the galaxy's own internal dynamics, like the gravity of the central bar or the spiral arms, and also by external influences like the gravitational tugs from satellite galaxies orbiting the Milky Way,
Yeah.
such as the Sagittarius dwarf galaxy, which has actually passed through our galactic disk multiple times.
Whoa, galaxies colliding, or at least interacting strongly.
Interacting, yes, and these interactions can stir things up, creating correlations in star velocities over vast distances, kiloparsecs even.
Kiloparsecs, that's thousands of light years, right? Huge scale.
Truly vast scales. So some of that velocity clustering might not be from a birth cluster, but from these later galaxy-scale dynamic events.
Okay, so how do we disentangle that? Can we tell if the shared motion is from birth or from later galactic stirring? This seems crucial for the hot Jupiter connection.
It is crucial. And this is where more recent work comes in, building on those initial findings and using even better Gaia data.
Let's dive into that. How are these newer observations helping?
Well, researchers like Cruson and collaborators in 2021, they used Gaia DR2 data, but also included radial velocities, the speed towards or away from us, to get the full 3D motion of stars.
Better data, better picture.
Exactly. And they were able to show that some of these phase space overdensities, these groups of co-moving stars identified earlier, do indeed seem to correspond to these large-scale ripples and streams within the galactic disk itself, not necessarily just old clusters.
Okay, so it's not just about the local star cluster anymore. The entire galactic environment, these huge structures, seem to be playing a role in grouping stars by velocity.
It appears so. The galaxy's structure itself imprints patterns on stellar motions.
What specific connections did they find between these large-scale structures and exoplanets, particularly our hot Jupiters?
One particularly striking discovery involves something called the phase space spiral.
The what now? Phase space spiral.
Yeah, it's a distinct feature seen when you plot the height of stars above or below the galactic midplane against their vertical velocity, how fast they're moving up or down. It looks like a spiral shell, winding up.
Okay. And what causes that?
It's thought to be a relic, a signature, of the Sagittarius dwarf galaxy, having recently passed through our galactic disk, maybe a few 100 million years ago. It perturbed the star's orbits vertically.
Wow. A galactic collision leaving a fossil record in star motions.
Pretty much. And Creason and his team found something amazing when they looked at exoplanet systems associated with this specific spiral feature.
What did they find?
They found that the exoplanet systems associated with this phase-space spiral have a ratio of hot Jupiters to cold Jupiters.
Uh-huh.
That is a staggering 10 times higher than what's seen in typical fuel star systems not associated with the spiral.
10 times higher, just by being part of this galactic ripple.
Apparently so. That's a truly massive difference.
It really forces us to reconsider the standard picture, doesn't it? It strongly suggests a powerful link between these galactic scale events, these dynamic features, and how common hot Jupiters are.
It absolutely does. It implies that the large-scale structure and history of the Milky Way itself can influence the types of planetary systems we see.
So how does this new finding, this link to galactic structure, help us solve the initial mystery of these misplaced giants? Does it replace the cluster idea?
Not necessarily replace, but perhaps complement or add another layer. It suggests maybe both mechanisms are at play, or that these galactic structures might somehow enhance or preserve the effects originating from clusters, or even cause similar effects independently. They also made another intriguing observation.
Go on.
Within these overdensity regions, whether they're cluster remnants or galactic structures, the ratio of hot Jupiters to cold Jupiters seems to increase with the age of the stars.
It increases with age. How does that fit?
Well, it fits with the idea that these galactic-driven overdensities, these waves and ripples, can persist for a long time, potentially billions of years.
Okay.
So it suggests that planetary system properties aren't just set at birth in a star cluster and then fixed. They might be continuously shaped or modified by these large-scale galactic processes throughout the star's lifetimes.
It's like the galaxy itself is a giant sculptor, subtly shaping the destinies of these distant planetary systems over vast timescales, maybe amplifying effects that started earlier.
That's a beautiful way to put it. It's not just the cradle, but the whole journey that matters.
Fascinating. Is there any other evidence linking a star's journey or speed to its planet?
There is, actually. Further research by Gaia and colleagues in 2021, again using Gaia and also Kepler data, looked at this from a slightly different angle.
How so?
They categorized main sequence stars based on their speed, their velocity, relative to the local standard of motion here in our part of the galaxy.
Yeah.
Sort of separating the fast movers from the slow movers.
Okay. And what did they find when they looked at the speeds of star systems with planets?
They found that the high-velocity planet hosts the ones really zipping along compared to the local average.
Yeah.
They tend to have a higher fraction of multi-planet systems. And the planets they do have tend to have lower average eccentricities, more circular orbits.
More planets, rounder orbits for the fast stars. Why would that be?
Their interpretation is that these faster-moving stars might essentially fly through the galaxy experiencing fewer strong gravitational disturbances.
Like they spend less time lingering in crowded or dynamically active regions.
Exactly. Fewer close encounters with other stars, less perturbation from giant molecular clouds or galactic structures, perhaps. This leads to more stable, dynamically quieter planetary systems, preserving their original architecture better.
That makes intuitive sense. A faster journey means less chance of bolting into trouble. What about the slower stars, then?
Conversely, the low-velocity stars, the ones moving more slowly with the local flow, appear to be more strongly influenced by stellar clustering effects.
Ah, aligning with the winter study.
Yes, it aligns well with the idea that slower stars are more embedded in or affected by the local density enhancements, whether from clusters or galactic structure, which can stir up their planetary systems, maybe leading to fewer surviving planets or more eccentric orbits, and potentially more hot Jupiters via those excitation mechanisms.
So it seems like a star's journey through the galaxy, its speed and trajectory, can also be a significant factor in how its planetary system evolves over billions of years.
It really looks that way.
Okay, so let's try to bring it all together. We started with the puzzle of hot Jupiters being too close to their stars. What's the big picture that's emerging from all this incredible Gaia data and related research?
I think the overarching picture is that our galaxy is a much more complex and dynamic environment than we perhaps fully appreciated before, at least in terms of its effect on planets.
More than just a backdrop.
Much more. It has these intricate spatial and velocity substructures, remnants of clusters, galactic waves, ripples, streams from past interactions. And these structures they aren't just curiosities. They appear to have a profound, measurable influence on how exoplanet systems form and, crucially, how they evolve over billions of years.
And the existence of these enigmatic hot Jupiters in particular.
Seems to be intimately tied to these environmental factors, whether it's early kicks in a dense cluster or later perturbations by galactic structures or maybe a combination. The environment seems key to getting those planets onto the migration pathways that lead them so close to their stars.
So the galaxy isn't just a static stage, it's an active player shaping these planetary systems.
That's the emerging view, yes. It's not just about how planets initially form around a single star in isolation. Their entire life cycle, their journey through the galaxy, the cosmic neighborhoods they travel through, the gravitational pushes and pulls they encounter, all of that seems to play a critical role in sculpting their final configurations.
It really broadens the scope of planet formation and evolution.
It does. And while we've made huge progress, especially thanks to Gaia's amazing data, truly understanding this complex interplay, the web connecting planet formation, star formation, cluster evolution, galactic dynamics, and even how the whole galaxy itself formed and evolved, there remains a major challenge.
A grand, interconnected puzzle.
Very much so. It's a deeply interconnected web of processes unfolding over cosmic time.
Well, this has been a truly mind-expanding deep dive into the strange and wonderful world of hot Jupiters and the surprisingly powerful influence of our home galaxy.
It's fascinating stuff.
It's incredible to think that these massive planets, orbiting practically on top of their stars, might owe their bizarre existence, at least partly, to long-ago encounters in stellar nurseries or the gravitational ripples from passing dwarf galaxies.
It certainly is. And it really highlights that planetary systems aren't these isolated islands we might sometimes imagine. They're deeply connected to and affected by the larger galactic environment they inhabit.
And the story isn't over yet?
Not at all. The ongoing analysis of Gaia data, with even more precise measurements in future releases, promises even more exciting discoveries. We'll keep refining our understanding of these complex processes.
It really makes you think, doesn't it? Consider our own solar system, just quietly orbiting here within the Milky Way. How might its long journey through the galaxy, through different environments over billions of years, have subtly influenced the characteristics of our own planets, even the Earth?
That's a great question. Maybe influences we haven't even recognized yet.
Yeah, just something to ponder as you gaze up at the stars tonight. Thanks for joining us on this deep dive.